Hello and welcome back to Calculus 2, section 10.6 on alternating series test. This is going to be our test number 8, and after this one we have two more, root and ratio, and that would conclude the list. So let's take a look at alternating series test. Before we jump into alternating series, we're going to talk about alternating sequence. So I'm going to take a look at alternating sequence -1 to the n, which is if you start your n at 0, is 1, -1, 1, -1, 1, -1, going forever. And alternating sequence is just the list of these numbers. It has nothing to do with sums or anything like that. It's just the list of positive ones and negative ones. Now you can multiply that with a value. Say you can multiply that with 3 and then get 3, -3, 3, -3, and so on. You can start it at a different value. You can go -1 to n plus 1, right? And if you start at n equal to 0, you will have -1, 1, -1, 1. You can do that. Or you can just use this one but start at 1. So there are many ways in which you can get this alternating sequence working. And as I said, you can also multiply by any kind of value and any number, right? And you will get the alternating sequence, which has, 3, -3, or 5, -5, 5, -5, and so on. Now, there are another two ways, right, to show the alternating sequence. We can have also cosine n pi. So cosine n pi is also alternating sequence, because the cosine, right, of n is going to be either positive or -1. I hope you remember your cosine graph. That's pi, that's 2 pi, that's 3 pi, and you see that the y values are 1, -1, 1, -1, 1, and so on. So cosine n pi is simply when n is 0, you get 1, -1, 1, -1, 1, and it's going to go forever. And you can achieve the same with sine. That's pi over 2. That's 3 pi over 2. That's 5 pi over 2. And 7 pi over 2. Going on forever. You get 1, -1, 1, -1 for y values, right? So it is going to be sine of n pi over 2. And n must start at 1. So, because you can't have 0, right? 0 times pi would give you 0, divided by 2 is 0, and sine of 0 is 0. So that would not be alternating. But if you have n equals to 1, then you get pi over 2. If n is equal to No, this is wrong. Because if n is equal to 2, then you get sine of pi, and sine of pi is 0. I have to rework this one. Let's fix it. So we will start at pi over 2 and add n pi. Can I do that? Not n pi over 2, just n pi. And start at 0. If n is 0, then we have pi over 2, and pi over 2 will give us 1. If n is equal to 1, the next value, then we are adding a pi, which creates 3 pi. Okay, there it is. So that's the one. Sometimes you have just to play with this a little bit. So these are the ways to come up with alternating terms. Alternating simply means it's positive, then it's negative, it's positive, it's negative, and so on. That's what alternating word, right, means. And very important, these sequences are bounded, but they are not convergent, because the limit as n goes to infinity does not have a finite value. More on that if you ever take, any of you, if you take advanced calculus, you will learn about subsequences, and then the theorem which says if two subsequences within of the same sequence, right? If two subsequences of a sequence have separate limits, then the main sequence is not convergent. But that's in advanced calculus. For you guys, just enough to know that it's not convergent because it doesn't go to a single number, right? It goes to two numbers at the same time. It goes to -1 and 1. All right. Now it's time to learn alternating series. Alternating series have a form of -1 to the n, an, and then infinity. So there is clearly the alternating term inside. Now, this can be replaced by these. It will be the same. So sometimes it's hidden, right? So for alternating series, we have, I like to draw like a roadmap on how you are going to compute these things. So let's see. Note that this does not belong to an. It's separate from an. Usually, right, so far, anytime I had an, it was everything that was within the sum. Well, this time, -1 to the n, the alternating part, doesn't belong to an. It's a separate entity. All right, so what do we do? So, procedure, I guess. Look at an only. Need an decreasing and limit an as n goes to infinity equal to 0. So these are the two conditions. So you have to check those. Condition number 1, condition number 2. So both true or something is false. If you get both true, you are then going to check summation of an. Observe that there is no alternating term in there. And now that series is either going to converge or diverge, leading to two outcomes: absolute convergence and CC conditional convergence. The other branch with the false over there leads to divergence. And that's it. That's the roadmap. So those two conditions that you check at the beginning determine whether you are on a convergence or divergence branch. And then if you are on a convergence branch, you have to check the sum of an, the series without alternating term. And if that one converges, you go in and label this as absolute convergence. And if that one diverges, right, it's still convergence. And this conditional convergence is a new creature that we did not have before. So for 9 tests, well, no, for 8 tests actually. So you have a divergence test, right? That one only shows divergence. Then you have other 8 tests which are either converge or diverge. That's absolute convergence. And then you have alternating tests here which will have absolute convergence, conditional convergence, or divergence. And I just need to understand what this means. Other than that, you can just follow through on this diagram and compute values. It's really straightforward. Let's take a look at, some examples. So say you have sum of -1/4 to the n, and then goes from, 1 to infinity. Doesn't matter. You can go from 0, you can go from 700, I don't care. So we are supposed to check this. Now, if I rewrite this problem, I will get 1 to infinity, -1 to the n, 1/4 to the n. So from here, I read that an is 1/4 to the n. So remember, it's everything other than the alternating term. Everything other than that. So what do we do? Well, the roadmap above says that we only get to look at my an equals 1/4 to the n. That's it. Check if it's decreasing, and check if it's if the limit is equal to 0, right? So those are the two things that we have to make sure to have in this particular case. So we can always start with the limit, right? That's the easier one. Limit n goes to infinity of 1/4 to the n is actually limit n goes to infinity of 1/4 to the n, which is equal to 1/infinity, right? And 1/infinity is 0. So this is satisfied. We have proven, right, that we have proven that we have a limit equal to 0. Now the next part is to see if if it is decreasing. Now, how do we know if it is decreasing or increasing? Like, what is the way? Well, you have two options. One option is to work with the derivative, right? You can find the derivative, and if the derivative is negative, then it's decreasing. That we learned that in Calc 1. Or you can just compare the terms. So you can say need an plus 1 to be smaller than an. That's what you need. Because if you have that hold, right, that shows that, see, that's the next term, right? It's n plus 1. That shows that the next term is smaller than the previous term, which means decrease, right? Because if every time you move to the next term is a smaller value, well, clearly decreasing, right? So I can just check if this situation holds. And if it holds, then we're good to go. Now cross multiply this, you get 4 less than 4 to the n. Oops, 4 to the n. Less than 4 to the n plus 1, that's going to hold, right? Because n are positive numbers, and n squared is less than n cubed, n to the 5 is less than n to the 6. So that it holds. So yes, it's decreasing. So now, since both conditions hold, we are on a convergence branch. See, we are starting with an, and both of these conditions 1 and 2 hold, both true. So we are on the convergence branch. We know that the problem is converging. Now the question is it absolute or conditional convergence? And we will check that once we run the final step, which is find the series, right, without alternating term. It's a roadmap. It's very structured. So the last piece of the puzzle is to figure out what's happening with this when I don't have my alternation term. But hey, you recognize that this is geometric series. You will always have something from one of the lessons we covered before, and you just go and do the series from whatever chapter or whatever section belongs to, right? So we found over here that R is a quarter. That's a convergent, which is less than 1, convergent by geometric series test. Geometric series test, give me 1 second. Have to reset the cooling for the server. All right, so now we have the geometric series test. So now we have convergence. So we can now write the answer. Since both conditions hold and summation an convergence, the series -1 to the, well, we had it differently written, -1 over 4 to the n converges absolutely. You can put AC, you can put CA, I don't care. Absolute convergence. That's the answer. So we technically are not learning new method of solving these. We are stitching a lot of old stuff together now to deal with alternating series. Let's take a look at another example. By the way, the lecture is over. If you want to tune out. If you are able to follow that roadmap and you know all of the previous tests, you are done. That's it. Now, I am planning on going through the next section. I did mention that yesterday. So make sure you're back when I restart the stream. Let's take a look at another problem. Say problem 24 from the book. Looks terrifying, which is why I love it. Negative 1 to the k, I'll use n, divided by n, ln squared n, from 2 to infinity. It's alternating series test because it is it has the alternating term in there, right? Also note that n equals 2, 3, 4 going on. So 1, 0, and negative numbers do not belong to our counting set that orders the sequence within the series. That's going to kick in later. It will be important. All right, so what is my an? My an is 1 over n ln squared n. That's my an. And I need to check two conditions. Condition number 1, limit as n goes to infinity of 1 over n ln squared n. Well, that's a big fat zero, because what you have is 1 over infinity technically, and that's 0. So we have that condition check, and now condition 2 is if it's decreasing. Again, you can compare terms, or you can do the derivative. So pick your poison, right? If you want to do the derivative here, you will have a double chain rule and a whole bunch of stuff. So let's try comparing the terms again, rather than going through the derivative of this. If comparing the terms doesn't work very well, if we can, conclude stuff, then we're just going to go back and do the derivative, right? Because derivative will work. You can always take the derivative. It's going to be a little bit work, right, to get it. So let's instead, right, let's try and compare the terms. So I need 1 over n plus 1 ln squared. Well, actually, I'm going to put the square on the outside. So ln of n plus 1 everything squared needs to be smaller than 1 over n ln squared n. I'm going to put the square again on the outside. So if we are able to establish this, right, we are good to go. Now, if it fails, then we have divergence, right? So cross multiply, we get n ln n squared less than n plus 1 ln n plus 1 squared. And at this point, we can compare them we can divide both sides. Remember, n cannot be 0, right? So now I can divide both sides by n, and I'll have ln n squared. So that's ln n squared. The whole ln is squared, to be less than, and over here I have 1 plus 1 over n, ln n plus 1 squared. So why did I do this? Well, I just wanted to have two things to compare. This one and that one. See, ln n is always smaller than ln plus 1. That's a given because it's an increasing function. But when you square there is the sweet spot where the left side is bigger. So ln n is always smaller than ln n plus 1. That's always, right, the whole domain. But when you square the two values, it becomes not true. Because if you square it, like this, then this is always true, and this is true on 1 to infinity. It fails between 0 and 1. Because 0 and 1 is a fraction, and when you square a fraction, when you take the ln of a value, you get a negative number, and when you square it, you get a very large positive number, because negative times negative is positive, right? So it doesn't hold for numbers for 0 to 1, but it holds for all numbers that are bigger than 1. And actually, those are the ones that we actually care about, because remember our problem started at 2? So see, this is important, right? If you started counting at 1, well, first, if you started counting at 0, you can't do the problem at all. But there are ways to modify this problem to actually make it, not work nicely. So this holds as well. By the way, this is always positive because you have 1 plus whatever value you get here, it doesn't matter. That's always positive, and then multiplies into another positive number there. So it's going to be a positive value, which is always bigger than the one on the left. So that's what we have for our comparison. And we know that the first two conditions hold. So now that means that we have to look at the series 1 over n ln squared n. And if this series converges, then we have absolute convergence. If the series diverges, we have conditional convergence. I still haven't explained much about conditional convergence. I will very soon, I promise. So just hang in there. So how do we do this problem? I'm asking you to type in chat. What do you think? How do I do this problem? Because this is old stuff. This is not what we're learning today. It's been 2 weeks since we learned this, I think. I don't know. Well, you guys are shy. Or you didn't get to study this yet, which is really concerning. It's integral test. We can integrate this. But before we can do integral test, we have to do those 3 condition check, right? Yeah. Condition number 1, decreasing. Well, we established that already. Number 2, positive. Well, yeah. Because n is bigger than 0. ln of n is bigger than 0 for n bigger than 1. And the square will only make the positive numbers anyway. So even if the ln of n was not 0, it doesn't matter, because we are on 2 to infinity. So all of these are correct, so it is positive, and the last one is continuous. You can do this in any order you want. So now we need to show that 1 over x now, because continuity, ln squared x is continuous. And how do we do that? Well, for continuity, we are recalling those two theorems and call on them from Calculus 1. If you go back to section 1.6 where we talked about continuity, you will find the theorems which state that x and ln x are continuous on their domain. That's the theorem from Calc 1. And then we say function combinations and function compositions of two or more continuous functions produce continuous function. So technically, the second theorem, that's also a theorem from 2.6. So technically, these two sentences establish continuity. The first one tells you that the participating functions, in this case x and ln x, two participating functions are continuous everywhere. So that's the first theorem. That theorem says that all of the polynomials are continuous, sine, cosine, e, ln, all of those functions are continuous. And then you have the four trig functions that are discontinuous, and you can make discontinuities, obviously, if you involve vertical asymptotes and so on. So what we have is all three conditions fulfilled, which means that I can look into the integral 2 to infinity of 1 over x ln squared x dx. Now this creates improper integral, which we know how to solve from your previous chapter, right? The one you took the exam on, that will be posted very soon in terms of the grades. And when I say very soon, I don't mean tonight, but possibly tomorrow. So we go limit b goes to infinity, integral 2 to b of dx over x and then ln x squared. This is a basic integral, right? Because we have, basic u sub, u equals ln x, du equals 1 over x dx. So I have du and I have u squared in here. So limit b goes to infinity, 2 to, I'm integrating it. No, still a substitute. 2 to b. We'll go back to x, so I'm not changing limits, because I still have to do the limit once I go back to x. So what do I have? I have du over u squared. So that's u to the negative 2 du, which is limit b goes to infinity. When I integrate this, I get negative 1 over u from 2 to b, but u is ln x actually. So I have a limit b goes to infinity, negative 1 over ln 2, no, b first, minus and minus makes a plus, 1 over ln 2. There we go, much better. So now this part is going to go to 0 because you have 1 divided by infinity, and you are left with 1 over ln2. Converges. So our integral converged, which means that our series of 1 over n ln n squared converges. And now that means again we have absolute convergence. So answer, since both conditions hold, and summation of an converges, in this case by integral test, the series summation 1 over n ln squared n 2 to infinity converges absolutely. So AC, absolute convergence. Just follow the roadmap. These problems look very complicated and very long. They are very systematic. You know exactly what to do when you see it. You see alternating term, you unleash alternating test. It's very, very structured. Now it's the time for us to talk about our friend over here, conditional convergence. And to understand that one, I will have to also dig into one of the series that we did before. So summation of 1 over n from 1 to infinity diverges by p series or integral test. This was done when I taught 10.4. This problem. That's old problem. What's a new problem? It's negative 1 to the n over n from 1 to infinity. So this is our new problem now, and we are just going to follow those steps. I'm not going to get overly excited, right, with anything. All I need to do is to follow those steps we had to check what's happening with this problem. So my an is 1 over n, and when you look at it, the limit as n goes to infinity of 1 over n is 0. And you also know it's decreasing because graph, right? Remember, we start at 2, so we're only looking for this part, and that's all decreasing. Can you take the derivative? Sure, 1 over x, the derivative of that is negative 1 over x squared. You have x squared, that's always positive. So you have negative 1 divided by a positive number. It's always going to be negative, therefore negative derivative is decreasing from Calc 1. So whatever method you know, whatever you're more comfortable with. Oh, guys, this is huge. This over here on the screen right now is huge. You see that harmonic series, the 1 over n, the top problem, harmonic series is divergent. And we have a proof for that. We did that problem back when we did integral test in 1.4. And we also have the p series to tell us it's divergent. But now, when I have alternating harmonic series by plugging in this negative 1 to the n, we have convergence already. We already have the convergence. So now all I need to do is to check summation of 1 over n, which we know diverges by integral test or p series. And that pushes us to conditional convergence. So answer. Now I need to explain this, I will. since both conditions hold and a series of an diverges, a series summation negative 1 to the n over n from 1 to infinity converges conditionally. So this is going to be now interesting to explain without screaming in the classroom. Let's see if I can calmly do this, but this is really exciting stuff. I love it. Your an does not have the alternation term. So your an leads to harmonic series, which gives you divergence, right? But these two conditions, when they pass, they give you convergence. So this convergence combined with this divergence gives conditional convergence. Guys, problem is convergent. Problem is convergent. What this does, it's only going to tell me whether that convergence is absolute or conditional. Now, why are we calling it conditional? Well, if you compare these two problems, right? If you compare the two problems, what do you see? You see that 1 over n is convergent under the condition that it's alternating. Otherwise, it's divergent. So you have absolute convergence, which is your convergence from before, and you have your divergence, which is your divergence from before. The new creature of this lecture, apart from the tree, the pathway to do it, the new creature is this conditional convergence. And conditional convergence happens when the problem converges because it passed the two conditions. Right? That's it. But the summation of an, which is a series an, diverges, in which case we have a conditional convergence. See, this is one thing where if you just compare, right, you see that the top problem that converged has the alternating piece in. So you can literally think about this as, conditional convergence. Under the condition that I have alternating term, under the condition that I have alternation, the series is convergent. Otherwise, right, it's divergent. So that's it. We have beaten this one to death. The next section 10.7 contains the last two tests, the ratio and the root. I'm going to do root first and then do the ratio. Now, I will have to have part 1 and part 2 for that lecture because I have to attend the meeting at 7:30 for food donations for food banks and so on. We have to figure out there are way too many people that are not working and not making money, and the stimulus was not enough and all of that stuff. So there are issues. I have a meeting for that at 7:30 scheduled with multiple people. So I'm going to teach root test prior to 7:30. And then that meeting should take about 30-40 minutes and so on. Then I'm going to come back after that meeting and teach the ratio test. I was thinking actually to schedule a separate lecture for root ratio test because maybe that would be better actually. Yeah, I'm only going to teach the root test tonight. Yeah, and then we're going to end at 7:30. And then I'm going to have a special lecture for the ratio test. Guys, ratio test is the test that we are going to use later in chapter 11. And we are going to use ratio test in differential equations. So you really need to know, out of all of these tests, I need you to know 3 tests insanely well. and those are geometric, divergence, and the ratio, where the ratio is the one that is going to appear in other courses. So I will restarting the stream right now. I will be back in less than 2 minutes with the root test, and then we'll figure out when we're going to do the ratio test. But it's going to be a separate lecture and not tonight. I'll be back quickly.